Okay, so the last little chunk for this first lecture, and it's really quite simple and quite quick. It's the basic components of a microcontroller, which I hope that you'll all somewhat be familiar with. I might sort of explain a little bit some of the relevant things that we'll use in this course, like in the course this semester, meaning more so the only thing that's very similar is memory. We're writing C, and so how we use memory or how memory is structured on the embedded system and on our computers is more or less the same, right? So the real-time challenges that you're going to get presented with in this semester will be slightly different. So normally we are making a game and we have to have some sort of, and the sort of deadline that we enforce is this frame rate, right? So you have to write code that can run or make sure that it synchronizes to 60 FPS or 50 FPS normally. But given that the performance in the virtual machine is so varying between systems and people's hardware, and it would be unfair of us to say we need you to all run a 50 FPS game, given that some people's laptops are probably not able to physically do that, given the software rendering of the virtual machine. We're going to scrap this and find out some other interesting way to challenge you. So we're still going to need to do real-time signal and event processing. We're going to make sure that is still a large part of it. Maybe do a bit more networking stuff. Like networking has a large sort of real-time component to it. And also the synchronization, normally you do a multiplayer game. We're probably going to try and have some sort of maybe a multiplayer style that will write a binary and that you can interact with this binary through sockets or something, but there won't be two boards or two games that are actually synchronizing with each other. But these are the normal challenges that you're presented with, is sort of getting two systems that can communicate and synchronize with each other in respect to time and in respect to a frame rate, right? So these are the normal challenges of like a game or a Game Boy style thing. But we're going to also sort of focus more on more of the software side of things, so we can maybe go a bit more in depth into these portions like event management, doing asynchronous communications, which I luckily wrote that library for, which will challenge a lot of you, making sure that we really get prioritization and scheduling done properly. Resource management will be a lot more challenging because given that we're on an x86 computer, we have a lot more resources, a lot more memory available to us, and so we can really push the envelope and use more of it, but as the more we use, it can be more complex to manage, right? So, a standard microcontroller. Where is my... Oh. Come on, where are you? So here we go. So, a standard microcontroller, meaning the little chip, will contain a processor. So the processor on most, like the boards that we would have used would have been an ARM. So this is the company and the architecture. So something like an ARM Cortex M4, what we would find on the STM F4 series boards, what we would have used, but it will also have integrated memory and peripherals. Memory being SRAM, flash, very equivalent to the cache and the RAM on your laptops, right? So these things are usually, they're on the processor, like in the microcontroller. They don't have external memory like you would find on Raspberry Pis, because these are sort of like the next step up in the like system on chip world. Microcontrollers are very small, everything on chip essentially. Well, at least the bare minimum you need. Peripherals being the different buses like I2C, SPI, DMA controllers, all these sorts of things. Timers, what else have you got? USB, Ethernet, essentially all the protocol, all the comm stuff. Anything else I can think of? No. Anyway, so, interrupt controller. There we go, right in front of me. So this is a basic architecture. You'll have your memory here. So this will be like flash. Oh wait, I'm going to shut my door. There we go, that back. And this here would be RAM. So essentially the thing is that flash is where your program, where your binary would be written to, and RAM is where like the sort of cache that you'll use to store and modify variables. This can be thought of similar on our laptops, is that flash is our hard drive and RAM is our, RAM is the 8 gigs, 16 gigs, 4 gigs, whatever you have, right? You have timers here. So timers, what they are in this case is a hardware timer. So we'll see in FreeRTOS that we have software timers. And what a software timer is essentially a process that counts, and then when it reaches something, it triggers an event. But the software, like, it counts in code, in that somewhere in the FreeRTOS sources, if we were to do a software timer in FreeRTOS, there would be some sort of like a count +1, plus equals 1, right? This is a hardware timer, right? And so what this means is that actually on the microcontroller, there is the clock, the crystal clock, is fed into a counter that counts up, and when it reaches some sort of a value, using what is called a capture and compare register, meaning it takes the clock value and compares it to some sort of a, hey, have I reached my total value yet? And when this thing is when this timer is counted up enough, it will trigger some sort of an event, which is an interrupt, and I'll explain them in a second. So the thing that makes hardware timers so powerful is that this counting is done from the system's crystal clock oscillation instead of in code. So it's not done by the CPU. So these timers don't actually use any of your CPU cycles, right? And so this makes them really useful for doing things such as generating periodic signals. Like, you can use them in PWM for doing signal generation, or for how is embedded systems that we would normally use in this course would work. They would use timers to generate the sys tick. And the sys tick is a periodic tick that is generated to interrupt execution of code and to call the scheduler, and which then decides what's going to run. And I'll go into this in more detail in the lecture next week when I kind of go through the inner workings of RTOSs, and more specifically the inner workings of FreeRTOS, right? So you have hardware timers, which do this, and what they do is they generally generate interrupts, or they can generate DMA interrupts as well. Like, they'll invoke other peripherals to do things at certain times, but they're used for doing timing that is not creating load on your CPU. So we have here our interrupt controller, and what an interrupt is, like going away from the controller itself, an interrupt is some signal that is generated to interrupt the CPU, right? So the CPU will be running some code, and let's say you have an interrupt on a GPIO pin that when you press a button, it will generate a signal that will actually interrupt the CPU, so the CPU will stop doing what it's doing, and it will handle the interrupt. And usually interrupts have certain signals. So you have this thing called an NVIC, which is a nested interrupt vector something. And the vector is essentially, you have this long, you have like a bitmap, a byte array, and like certain flags will be certain interrupt numbers. And then when a certain interrupt is called, a certain function is called. So when you have a GPIO interrupt on GPIO port C, you press the button, GPIO port C's interrupt handler function will be called. So in this way, you can imagine that instead of checking if the button is pressed, your CPU doesn't have to waste time checking it. It will just wait until the interrupt signal comes, and then in the interrupt handler, you can say, yes, set the LED on or something, right? So it's again this sort of offloading of CPU of work that the CPU would do to peripheral hardware, right? Obviously, CPU is the CPU. Here we have I/O ports and serial ports. So I/O ports can be GPIOs, UART, this is UART, all the different peripheral comms and whatnot. But essentially, it's just a way of sending binary data out via high and low signals, right? So this is the basics of the microcontroller. If you go into the very complex of it, you'll see you have, like, for instance, your SPI comms, you have your GPIO ports. These will be somewhere connected to the NVIC, if I can find it here somewhere. NVIC, you have a real-time clock, power management, camera interface, USB, flash, RAM, external memory controllers, no. So we have the actual M4 core, DMA controllers here, debug interface, timers, UART, serial, temperature sensors. Where is the NVIC? Maybe it's not on here as an actual reset clock control. But these are all things that you'll get exposed to in the future. Mostly, I know there's some really good courses at TUM in your masters that will sort of go into the more specifics of this stuff, right? So to summarize, these are also weren't mentioned. These are a secondary function of these general purpose pins. So here, I wonder if it's written on here anywhere. But what ADCs do is that on the board that you would have been given if you were to do this course at TUM is that it has a joystick on it, and the joystick is essentially a potentiometer, so like a variable resistor that goes between 0 and 5 volts, and the voltage that's sensed on the pin is converted into some digital value between, for instance, on a 12-bit system, it's between 0 and like 12,200 or whatever the 12-bit maximum value is. And so it's a way of converting an analog signal into digital, and you can also find I've selected the wrong one here. So this is ADC, DAC, DAC, digital to audio, digital analog conversion. Wait, no, I was correct the first time. Sorry, long day. ADC, analog signal in, digital signal out. Reverse it around, you have digital signal in, analog signal out. So a DAC would be used for converting digital audio, like a PWM wave, something like this, where you have like, this is a terrible PWM wave. Something like this, where you have different pulse widths, and you convert this into some audio signal, right? So this is a DAC, and an ADC is the process of converting this into this, and it sort of samples it, right? Anyway, so buses to communicate, I think I've kind of covered all of this. But anyway, so this is what we would have been dealing with, what we won't be. So you would have had these two boards. So this is one single board. We'd have some display that will communicate via the SPI interface, which you can see here. So this is the SPI, which is one of the, pretty much one of the most common embedded sort of peripheral communication protocols. And you would have had this sort of joystick and the buttons. Now this here we have replaced in the system that we'll be using with the keyboard and with the mouse. So you won't have an ADC, but you'll essentially be able to, the backend library will request the coordinates of the mouse on the screen. And as you can imagine, there's some sort of a varying value, right? This is the board that you would have used. If you don't complete this course and you do it next semester, you might be able to work with these. The stack I explained in the setup lecture, which went through before. This is also not relevant for this. This is also not relevant for this, except for here. So programming style, there's a style guide in one of the PDFs. But if you want to learn to write really good C, I personally would recommend you to go and find the Linux kernel style guide. It's actually a really good read. You'll learn more from that style guide about writing good code than anywhere else. Like on just sort of practices, the whole idea of writing good style is good. Styled code is easy to share and read, but also from like humans are really good at seeing patterns in things. And if you write the same code patterns all the time, as soon as you write something that doesn't fit the pattern, meaning like you've written a mistake, you'll generally be able to pick it up a bit easier, right? Also things such as modularizing files. I'll probably do a bit of a tutorial on writing modular code. So files of like 20,000 lines, you don't know where to start, where to look at, where to find things. But if you modularize things, like if you want to write code just for the screen, then you know that if the screen's not working, there's a good chance that your error's in your screen file. Or you can maybe reuse the screen if you're doing the screen code, if you're doing a project using the same screen again, right? Things such as comments. So here, Comments should be like describing the functions themselves. Like each little function should have a header where you describe what the function does. But then also there's sort of like over commenting code. Like if you just incrementing a variable by 1, you don't need to write a comment incrementing variable by 1 because that's obvious. Like you can also, good, well-written code should in a way document itself, but maybe instead of saying incrementing variable by 1, you can sort of give context, like saying the variable is incremented by the number of bits that we got in, which in this case was 1. So it's giving context to where this 1 is coming from, that someone reading the code wouldn't necessarily see straight away, right? Naming conventions are also quite important. Different companies and different projects, like the Linux kernel, will have its naming convention. Generally, and also your style will be marked in this course, is that obviously we're not giving you a style guide saying, hey, we want camel case, function names, snake case, variable names. You just pick one that you like, stick with it, right? Generally as well, things such as if you have modularized file, then you have like a screen file, like something like you have lcd.h, then all of your functions should be some like lcd and then some function name like update, right? And this will be some function you have. Because if you have this function with this prefix of LCD, so all LCD functions have the prefix LCD, then it's pretty self-explanatory that this function does something with the LCD. Things like this should be, you should really make a habit of them. Like, especially now if you're beginning your computer science career now, really try and make a habit of these things now. Not important for this semester, not important for this semester. Next steps, not important for this semester, not really. You could do this, read through the manual. So the manual has some things on setting up with a project, so ignore that stuff, but also has stuff like style guide, read the demo project code. Essentially the structure is that this week, you'll do a Git tutorial that will then, and then we'll start going on to the exercises, which actually start working with FreeRTOS. So the demo code is applicable for the FreeRTOS projects, and as such, you don't really need to read it now, but more so in like a week's time. The Git stuff is a bit separate. It's more like learning to use Git, then you know how to use Git so you can use it for the rest of the semester. So the first exercise is this Git tutorial, and so how it works is that you have to find me on GitHub, find my profile. You'll find a pinned repository called Git tutorial. Create an account, log into your account, and fork it. So when you do is you'll go to my page, go to this page with Git tutorial, and there'll be a fork button, and then it will create a fork. And so the fork is a clone of my repository that is yours. You own it. And the thing that is different between forking a repository and just cloning it is that you can then actually push, like you can save your changes on GitHub so that it's safe and whatnot. And this is what we're going to need to see from you, is that you're using Git properly in this introductory exercise. So in the README, if you go into the GitHub page for the Git tutorial, the README is the text that will appear on the first page. Just start reading it. It's a lot of text, I know, and I'm sorry for anyone that really hates reading, but hopefully at the end of reading it, you'll understand Git, you'll understand CMake, and you'll understand the basics of compiling code. Now, I can't emphasize enough, if you want to get into C development, how important understanding how code is compiled is. It's very simple when you get down to it. Obviously not like on a compile level, but on like putting together a build system or putting together a project, it's not very involved. But once it clicks, you will be able to put together any project, pull random code off the internet and get it to build. And doing that is one of the best skills you can learn in C development, being able to build code. So anyway, extra resources, I would say maybe look at the slides from the setup lecture, because they're sort of a more fleshed out version of this. Some of this stuff is not, no, this is all, oh yes, I'll put this up as well, or maybe it's still up there. I also I was doing some teaching in Singapore, and I did one quick exercise on basic C stuff where you can sort of create variables and do some pointer stuff. So if you're a bit unsure of your C knowledge, maybe go and check out this. I'm not really going to demonstrate it myself or run through it, but there's a PDF and there's some example snippets, and I think there's actually some code. So you could do this to sort of freshen up a bit. So anyway, that is the beginning of this one. So I think I'm going to call it a day now because I can barely feel my throat anymore. I'm going to record the Git tutorial tomorrow and we should be golden. So hopefully I can get these lectures chopped up and stuff. If you have any questions, because obviously this is an offline recording, how I'm going to do this is I'm going to put up a time slot for and I'll sit in a chat room, essentially like a video chat, and you can come and ask me questions. So if through these lectures you had any questions, write them down and I'll put up a time when I'm online for one-on-one or one-on-group sort of question answering. So thank you for your attention and I will see you in the next one.